So we'll begin today with a very interesting problem in fluid mechanics called the hydrostatic paradox problem. Okay. Of course, it's just a paradox for the namesake. Actually, the problem can be very well explained by the concepts of physics. But anyhow, for historical reasons, this is called the hydrostatic paradox problem. So the idea in this is like this, that we have, let's say, three containers which are of identical base area. Like this, let's say. But having different overall volume, because one of the containers is conical and increasing in cross section as you go up. The second one is, let's say, a perfect cylinder. And the third one is like a tapering conical vessel, like this. Okay. And all three have been filled up to the same level with the same ideal fluid. So it's a comparison of various physical quantities related to a static fluid in these three type of containers. Okay, so what we've done is we've gone ahead and filled these three containers, the open containers, right up to the same level with the same liquid, let's say water, same ideal fluid. And the three containers have the same base area. Also, apart from the fact that liquid is filled up to the same level in all three of them. Yeah. Okay. Yeah. So that's the problem, that the containers have a common base area, let's say A, and all three of them have liquid filled up to the same level of, let's say, H, and that to the same fluid. So let's say these are containers 1, 2, and 3. So open containers 1, 2, and 3 are of identical base area. Filled up to the same height with the same ideal fluid. So if weight of fluids are, say, W1, W2, and W3, and the normal reaction force on the base of the container due to the fluid pressure are, let's say, N1, N2, and N3. Then we have to suggest which of the following are correct options. Okay, so just suggest which should be the correct option. There's a more than one option question. So yes, okay. So Naman, check your answer. Kevin, your answer is correct. Piyush, check your answer. Tanishk, correct. Aditya Bansali, correct. Pranaya, correct. Okay. Now, once you get the correct kind of contradiction, there seems to be some kind of paradox. Okay. Because the correct answer will indicate that normal reaction is not equal to weight. So when you take the body of fluid as a free body, okay, how do you explain that? That the normal reaction acting on it because of the floor or because of the bottom surface does not always equal to its weight, or should not be equal to its weight in every one of the three cases. So there is the apparent paradox, okay, but it's solved very easily by considering the proper application of forces. Yes, very good, Snikita, that's correct. So the concept we'll apply here is that weight of the fluid is equal to mass into volume. I mean, density into volume into G. In the case of the containers, you can see volume of liquid in container 1 is greater than volume of liquid in container 2 is greater than volume in 3. So definitely W1 should be the greatest and W3 should be the least. Okay. So out of these two options, you can see that this option is wrong, whereas this option is correct. But then at the same time, when you consider the normal reaction on the bottom floor of each container, you can see that the normal contact force because of hydrostatic pressure, they should be equal to pressure into area. So that should be equal to rho gh into area, whatever that base area is. So from this, what we figure out that same level of water in each one. So N1 should be equal to N2, should be equal to N3. So this explanation should suffice to understand why B and C are the correct options. But at the same time, it should also suggest you that there is something more interesting happening here. When you consider the free body diagrams of the liquids, just the body of liquid, you consider it as an FBD in each of the three cases. So whatever contact force the liquid applies on the bottom surface, the surface has to apply equal and opposite normal contact force. And of course, if the weights, they're like this, okay. But now you have to also understand that as far as the side walls are concerned, in this case, the side walls are applying force due to pressure like this. So there is some net force, let's say F, that is acting because of the side walls. This is net force. Okay. So in this case, what is happening is that W1 is balanced by this normal reaction plus F. Whereas in the second case, the side walls are applying forces which are like this. So the net force due to side walls is 0. So in this second case, what is happening is that the weight is exactly balanced by normal reaction. Whereas in the third case, the side walls will be applying force like this. So they'll be applying a net force. If you see the vector sum by symmetry, the horizontal components will cancel, the vertical components will add. So let's say that's F prime. So again, F prime is the net force due to side walls. And you will see that that cancels, I mean, that adds vectorially downwards. So in this case, what is happening is that this weight is equal to this normal reaction minus the force that the side walls are applying. So from this analysis, now what we can understand is that N1 is equal to N2 is equal to N3, which is equal to rho GH into A. But out of this, only N2 is actually equal to the weight of the fluid. Whereas in the first case, the weight is greater than the normal reaction. In the third case, the weight is less than the normal reaction. So this was a proper explanation of the hydrostatic paradox problem. It was a problem originally thought of by ancient philosophers before the proper vector calculus method and Newton's laws and all this had been invented in physics. So at that point of time, it was a paradox, but of course, this is the correct explanation for it. Exactly, Aditya, that's correct. Okay, your analysis is correct. So as you can see in the second container, the weight exactly equals to the normal contact force. But in the other two containers, that's not the case because there is some net interaction between the the slanting walls on the side of the conical vessel with respect to the body of liquid. Okay, let's move on to another question. Now, last time we were also discussing, if I remember, we had discussed a little bit about Pascal's law. Let me just check, or we had not discussed. No, right. We had not started with the discussion of Pascal's law. We just seen the net force due to pressure and the torque problem and all that. And before that, the barometer and manometer. Okay, so let's look at the next property of a static fluid, of an ideal fluid which is at rest. Okay, so the next thing, the next principle we'll study is Pascal's law. The statement of Pascal's law, I'm sure you know, it suggests that any change in pressure created in a fluid is transmitted equally to all points inside it. Okay. So for a static fluid, any change in pressure. Now, obviously, this change in pressure is due to some external effect. So this one is transmitted uniformly to all points inside the fluid. So at the outset, it looks like something very obvious and simple, but let us understand the full implication of this. So for example, let's say we have a sealed jar. Okay. So this is an airtight container. Now let's say we had originally filled liquid up to some level like this inside. Okay. But before sealing the container from above, we had not removed any of the air. So its above part is containing air at atmospheric pressure. Okay. So then you can see that the pressure at any point inside like this, which is at a depth of h, in this situation is equal to atmospheric pressure plus rho gh. Okay. But next, let's say what we do is we take the same sealed container with the liquid and the air and all that, and we attach a vacuum pump, okay, to remove some of the air from above. So it's still got air, but the density of air is now got less because we've attached a vacuum pump, okay, You can even remove all that, but I'm just saying here. So suppose we have now pumped out some air such that this now has an air pressure just changed to T prime equal to, let's say, P naught by 2. So you can see that the pressure at the surface of the liquid, for example, the pressure at the surface has changed to how much? It has changed from P naught to P naught by 2. Okay. So there is a change in pressure at the surface of minus of half of the atmospheric pressure. Now, if you look at that point A again, the new pressure at that point A will become the pressure at the surface plus rho gh. So this time the pressure at the surface is P naught by 2 plus rho gh. So if you look at also at the point A, the change in pressure is the same. The final value of pressure minus the initial value, it is again minus P naught by 2. So the change in pressure at any point inside the liquid, A could be any point inside. So all points inside the fluid will experience the same change in pressure because of some external effect. So this is a very basic example of how Pascal's law basically works. Now the main thing is this principle can be used very effectively to create changes in pressure which might be mechanically useful. One example of that is the design of any hydraulic system, particularly hydraulic lifts, etc. So this is a very useful mechanical property of this kind of a system, where changes in pressure can be manipulated by very easy external causes or external changes, and those changes in pressure can be transmitted to different points inside a fluid in a very effective manner, okay, to create desired results and to create mechanical contraptions. So that is the importance of Pascal's law. So hydraulics is actually quite an important branch of mechanical engineering. Okay. Many heavy machinery or heavy engineering based mechanical systems have hydraulics within them or hydraulic systems within them, that kind of heavy engineering equipment. Okay, so let's understand how, for example, a hydraulic lift works. You would have also heard of things like hydraulic braking systems, etc. That's all part of that same branch of mechanical engineering, which is hydraulics. So let's say we have got two columns that we can fill with liquid, which are connected below. So it's the same body of liquid filled up in both the columns. So let's say we've got some kind of an ideal fluid now. It's filled up like this over here. Now let's also say that there are two pistons which are floating on the liquid here and here. And these are movable free pistons. They're also lightweight. This one has an area of A1 and this one has an area of A2. Now, if we apply some force over here, it could be used to balance the weight of a heavy object. Because ultimately, the production of this force over here will increase the pressure at this point. Okay, let's say this point is B and this point is D. So that will change this, that will create the same change in pressure at the point D. So pressure at the point D should be equal to pressure at the point B. So pressure at the point D will become atmospheric pressure plus the weight of that object divided by the area of cross section there. So this should be equal to, on this side, atmospheric pressure plus whatever force we are applying divided by A1. So you can see a force of mg multiplied by this factor A1 by A2 is obviously less than 1 in this diagram. This force can be used to, this force can generate enough pressure to balance this weight. Or using this force, if we press this slowly downwards, this weight will be lifted slowly upwards. So smaller amount of force can be used to lift a larger amount of weight. So this is one example of how a hydraulic lift works. So for example, if E2 is equal to n times A1, where obviously n is greater than 1, then the amount of force you have to apply to lift the weight on the other side is mg by n. So it creates a sort of a mechanical advantage kind of a situation, like a system of pulleys. Okay. Now, where this is also very versatile is that it can also create a, we can also have a situation where the direction of the force we are applying versus the direction of force which is generated can be manipulated very effectively, because pressure is a scalar quantity, whereas force is a vector quantity. So this can be taken advantage of in a hydraulic system. So for example, you can have a piston over here, which is of area A1, and another piston here, which is of area A2. And this region is filled with an incompressible fluid. Okay. So a comparatively lesser amount of force here, F1, will generate a comparatively larger amount of force here, F2. So ultimately, F1 by A1 will be equal to F2 by A2. So this is another example of a hydraulic system. Okay. Scale models of hydraulic machines can be created very easily using simple things like surgical syringes and small tubes and things like that, and cardboard boxes, or containers, plastic containers, etc. If you just search through YouTube, you'll see a lot of high school level projects done where they make scale models of robotic systems or mechatronic systems using hydraulics. So anyhow, that is the working principle of hydraulic systems, which is Pascal's law basically. Okay, next up, let's look at a quick numerical example with a kind of application of, you can say, either Pascal's law or just the basic concept of pressure gradient, hydrostatic pressure gradient, whichever you choose to call it. Okay. So we have a, let's say, an open glass tube or something like this, which we have filled with some liquid, like water, for example. So initially it's filled with just water. Up to some level like this. This is water at a density of 1 gram per cc. And also the height of the water column on each side is h0. And this length is L. Okay. Now next up, what we are going to do is, from one side, we are going to pour another immiscible liquid. And let's take the case where the immiscible liquid is something lighter than water, like kerosene oil or something. So next, what we do is, So that's going to create some change. So from this side, let us say we have poured in another liquid like kerosene. Such that the level of kerosene on this side is X. That is an example of an immiscible liquid which is lighter than water. So let's assume this is 0.6 gram per cc, the density of kerosene, or the relative density is 0.6, let's say. Now, as a result of that, what will happen is that the level of water on this side would have gone down. So it's now gone down in comparison to H naught to some H1, and the level of water on this side would have come up. So let's say on this side it has come up to some H2. Okay. All right. So given that H naught was equal to, let us say, 50 centimeters, L is 100 centimeters, and X is equal to, now let us say, 40 centimeters. You want to find H1 and H2. So you can see that the density of water given to us is the standard value 1 gram per cc, whereas the density of kerosene is 0.6 gram per cc. That's not probably accurate. It will probably be more like 0.8 or whatever, but let's take for this problem as 0.6. Okay. Both of these are stationary. Okay. So these are open glass. There's an open glass tube which is bent into a U shape like this. Open glass U tube of uniform cross section. You could just send me the answers quickly. Okay, Harpriya, I'll scroll back up. Just try out this question first. Okay, so let's see. So H1 according to me should become 38 centimeters and H2 should become 62 centimeters. Yes, Kevin and Snikita, your answers are correct. Okay. So let me tell you the method that I would use. Maybe there is an alternate method also. You can tell me if there's anything. So I would just equate the pressures of these 2 points first. That would give me one equation. Okay. And the thing that I have to be careful about here is when I'm equating the pressure at 2 points, they should be in the same horizontal level for the same liquid. Okay. So mind you, we cannot equate the pressure at a point like this with a point like this because they are different liquids. So we cannot do that. Okay. So here we cannot compare C and D because C is in kerosene and this is in water. Okay, but we can compare, but pressure at A will be equal to pressure at B because they are both in water. Okay, at the same level. Okay, so having understood that, now as far as the pressure at A is concerned, we will again have to break down the column of liquid above. So now we'll consider, let's say, a point like this E, which is at the interface of kerosene and water. So using that, now we can say that the pressure at the point E will be atmospheric pressure plus density of kerosene into G into X. Okay. And then if we compare E and A, treating them both as if they are in water because it's just at the interface. This is okay. So ultimately we can see that the pressure at the point A should be equal to atmospheric pressure plus density of kerosene into G into X plus density of the water into G into H1. Whereas B is very direct. The pressure at the point B we can compare with the column above and see that it is atmospheric pressure plus density of water into G into H2. So now implementing this relation from here, we'll get that density of kerosene into G into X plus water into G into H1 is density of water into G into H2. So this will give us a very effective little equation that H2 minus H1 is equal to the relative density of kerosene with respect to water into X. So in this case, it will come out to be 0.6 into 40. So the difference of the two levels, H2 minus H1, according to this, should come out to be 24 centimeters. Okay. Now you also have conservation of volume of water. So you can see that volume of water, before putting the kerosene, it was 2H0 plus L into whatever cross-sectional area, let's say S. Okay. So that should be equal to H1 plus H2 plus L into S. So this is telling me that the sum of the two heights should be equal to 2H0 or H1 plus H2 should be equal to 100 centimeters because H0 was 50. So this is my second equation. Okay. Now solving H1 and H2, you'll get what we just discussed. You will get 38 for H1 and 62 for H2. Okay. Now anybody thought of some other type of method over here? What is the relationship between kerosene and water apart from the fact that they are immiscible? Kerosene is lighter by a factor of 0.6. No? So a column of kerosene, which is of height 40 centimeters, an equivalent column of water would have been of how much height? 24 centimeters. Okay, now instead of putting kerosene, if I put water from one side, the level would have equalized on both sides. No? So that extra 24 centimeters of water would have caused this one to go down by 12 and that one to go up by 12. So we could have, just by thinking of equivalence of kerosene with respect to water in terms of pressure gradient, we could have thought that make it an equivalent problem, that instead of X equal to 40 for kerosene, take an equivalent amount of water, but that equivalent amount of water would have a level of water of 24 centimeters. So we added 24 centimeters from this side, it would balance out on both sides. So H2 would have become 50 plus 12 or 62. So that's an alternate way of understanding the question. Okay, so anyhow, so solving equation 1 and 2 will give you this final result. That's about Pascal's law application. All right, we'll have to note down the above part, so just give you some time. So in case you had not written down this part, right, this is the part Harpriya and I think it was Aman, right? Amog. Harpriya and Amog, this was the part you had to write down or above this? Okay, okay. Now in the meantime, question by Ayush. Disadvantage of using hydraulic systems. It's more about what is more convenient for a given application. Hydraulic systems, typically you have to use very high density fluids and they are used in heavy engineering. Whereas, for example, using a system of pulleys for mechanical advantage, uh, it is more convenient where your systems are vertical, so you're making use of gravity also. Right. So typically hydraulic systems are suitable for like heavy engineering applications of mechanical systems. Okay, so I'll just scroll down a bit now. Okay, so that's done now. Right. Now we aren't completely done with the concept of pressure gradient. We'll come back to pressure gradient in non-inertial systems also. But continuing ahead with a fluid which is static in ground frame, or at least static in some inertial frame, let's look at the next property of such a fluid, which is the principle of buoyancy, or the property that when we dip any body inside the fluid, whether we submerge it completely or just dip it partially, the fluid will apply an upward force commonly called upthrust or buoyant force. So that property of the fluid is called buoyancy. And that principle was first discovered by Archimedes in what I'm sure you know as a very funny incident of a eureka moment in physics. So anyway, it is attributed as Archimedes principle. So Archimedes principle gives us in words the exact amount of upward force or upthrust that a submerged body experiences in a fluid. So the statement of this principle is like this, that any body submerged, okay, it might be partially submerged or completely submerged in a fluid, experiences an upthrust. So the term upthrust is self-explanatory, a thrust or a force in the upward direction, but this is also called buoyant force because that property of the fluid is called buoyancy, vertically upwards. It experiences an upthrust equal to, so it's precisely equal to the weight of fluid displaced by it. Okay. So when such a body is submerged in a fluid, because certain part of its volume has now been submerged inside a fluid, so an equivalent volume of fluid gets displaced from that position where the body's submerged part is located. So the weight of that much portion of fluid exactly that has got displaced, that weight is exactly equal to the amount of upthrust that the body experiences. Okay, so one way of expressing this mathematically is that the upthrust or buoyant force equals to density of the fluid multiplied by volume of the submerged part multiplied by acceleration due to gravity. That is the weight of, so this V sub, this is nothing but the volume of the portion of the body which is submerged. So in case of complete submergence, it's the total volume of the body. In case of partial submergence, is that part of the volume which is submerged. Okay. So based on the Archimedes principle statement, we can now develop this direct formula for buoyant force. Okay. So we just write it like this, that buoyant force is equal to density of fluid multiplied by volume of submerged part into G. Okay. Now, of course, Archimedes had developed this principle or realized, or you can say discovered this principle by just logically analyzing what happens in terms of the interaction between the submerged part of the body and the fluid in terms of pressure. But there's a very simple way of deriving this also from the concept of pressure gradient, which we'll be doing next. So Archimedes had basically discovered this principle just by logical analysis, okay, of the interaction between the fluid with respect to the part of the body which is submerged. Whereas we will see that there is actually a simple mathematical derivation for this based on the pressure gradient concept. Okay, now a simple proof of this can be understood if we just apply this concept of pressure gradient and the force due to pressure on a rather symmetrically shaped body. So for example, I have a situation where, let's say I've taken a solid cubical metallic block, okay, and I have kept this completely submerged inside water by suspending it using a thread or something. It's rather easy to prove in such a symmetrical kind of shape that the upthrust will be equal to the weight of the equivalent amount of water, that is a cube of water, which would have been displaced by this solid cube. So suppose I have this situation, as I was saying, this cube is completely submerged under water or under some fluid by means of a rope or a thread or chain or whatever like this. So this is an ideal fluid of density rho, let's say, okay? And this is a solid cube of dimension L by L by L, and it's submerged like this. So what Archimedes Principle tells us that the tension in this thread now will become less than the true weight of the object, because the water also ends up, or the liquid also ends up, applying an upward force on this, which is equal to buoyancy. Okay. So according to Archimedes Principle, the tension should be equal to mg minus buoyant force, where the buoyant force should be equal to density of fluid into L cube into G. It's equal to the weight of fluid displaced by the cube. So the cube displaces an equivalent volume of water, which is equal to its own volume. So that's L cube. But that volume of water has how much mass? It has density of water rho into L cube. So that should be equal to the upthrust or buoyant force. Now let's understand the proof of this. So where does the buoyant force actually come from? It comes as a result of force due to pressure on each of the surfaces on the cube's surfaces applied by the water or applied by whatever fluid we have over there. So very simply, if we just visualize this like this, that this cube is kept under water or under fluid such that this surface is at a depth of h1, right? And this surface is at a depth of h2. So you'll see that this surface will be experiencing a downward force F1. This surface will be experiencing an upward force F2, whereas the side walls will all be experiencing some forces F, which will balance. So the net of the forces on the four sides will be zero. The resultant of the four, because they cancel in pairs, but F1 plus F2 is not equal to zero. This is the force on the upper surface. And this is on lower surface. In fact, from the concept of pressure, you'll realize that the magnitude of F2 is greater than the magnitude of F1. So that's why the net force, which is the buoyant force, will be equal to F2 minus F1. Okay. Now, what is F2? It is the force due to pressure at a depth of H2. No? So that will be equal to how much? Rho G H2 into the surface area, which is L square, because it's a cube. Whereas what is F1? So in this you can see F2 will be the pressure at that depth into the area. So that is rho G H2 into L square. And similarly, what is F1? It's pressure at that depth into the same area. So that is rho G H1 into L square. So now when you substitute the values of F1 and F2 in this buoyant force equation, you will see that you will get the value of buoyant force as predicted by Archimedes principle. So you can just note this down and fill in these last steps. Okay. So obviously I said that this is a simple proof of it because we're using a symmetrical shape like a cube, and also I've kept it completely submerged. Okay. But in the case of the cube, even if I keep it partially submerged, that only a certain part of that vertical height L is submerged inside the liquid, it will be quite easy to prove that it's equal to the mass of liquid displaced into G, or weight of liquid displaced. But if I take a random shaped object, like a randomly shaped rock or something like that, then the proof is a little bit more complicated. We'll have to involve calculus a little bit, but nonetheless, it comes from the same principle. So just note this down. We'll discuss the other cases also. Note this down and complete this derivation. Okay. So the moment you substitute H2 minus H1 as the side length of the cube L, you will see you will hit this value. Buoyant force's value will come as predicted as predicted by Archimedes principle. Okay, so sure you people have worked out the steps here. So this buoyant force should be equal to pressure difference into the area of cross section, which is common for the two surfaces. So density of the fluid into G into L square, which is the area, but into L, which is the height difference. So it's ultimately equal to, it is equal to density of fluid into volume of the submerged part, because it's the total volume only over here, into G. So that's weight of fluid displaced. Now like that, you can very easily figure out that if I have a slightly different situation here, that I've suspended the object in such a way that it's only partially submerged. Okay. But it's the same symmetrical shaped object. It's a cube. So it's again reasonably easy to show that our buoyant force will be equal to weight of liquid displaced only. But this time the submerged part volume will not be L cube. It will be some fraction of it because it's not all submerged. So suppose we repeat that same experiment, but with the level of liquid, or rather the object is not completely inside. Okay, it is only up to a certain fraction of its side length is submerged inside. So this is still the same object three-dimensionally. It's the cube of dimension L by L by L. But only this part of it is underwater or inside the fluid. So density rho. So now let's take this section of height x. So again, when we talk about the forces acting on it, there will be some different tension this time, same weight, but different value of buoyant force. So this time that tension will be equal to the same weight minus a different buoyant force. Now this buoyant force should be equal to density of fluid into volume of the submerged part into G. So by Archimedes principle, this should become rho into x into L square into G. This is what we are getting by Archimedes principle. Direct application of the statement. Okay. Now let's prove why that is the case, because ultimately again buoyant force is basically what? It is the resultant sum or resultant force due to pressure on the 6 surfaces of the cube. So once again, the force due to the side walls or the force on the side walls, they will all cancel in pairs. But what only survives is the force on the top surface, let's say F1, the force on the bottom surface F2. Now this time F1 will be atmospheric pressure into L square, whereas F2 will be pressure at this depth, is at a depth of x, so it will be P naught plus rho gx into L square. So the moment you figure out from here that buoyant force is F2 minus F1, you can see it is rho gx into L square, which will connect you with this concept. Okay. So as I said, even this is a very simple proof because we have taken the shape of the body to be as symmetrical as possible for us, which is the cubical shape. Now, what happens if we take a more general shape or a very arbitrary shape like an odd-shaped rock or something like that? So it has no particular symmetry to it. So we'll have to involve calculus a bit, but the idea will be the same. Okay, so Vineet, I'll just scroll up a bit so you can write down these two results together. Those of you who have finished writing this down or figuring this out, now start thinking of what kind of steps I could apply if I change the diagram to this. I have some odd shaped body like this now. Okay. And that I have kept partially submerged inside a liquid. How would I prove for this kind of case that again, the buoyant force should be equal to the weight of liquid displaced? It's a little bit more complicated, but there should be some way of proving it. So let's understand that. So it's basically going to be a good small little exercise in calculus for us. Okay, so we'll see that the general derivation really involves a bit of thinking in calculus, okay? But at the same time, it's not so difficult either. So let's say I've taken some arbitrary shape like this, and some part of it is submerged underwater, like this. Now I'm really just concerned with calculation of the buoyant force. So I'm not going to concentrate so much on the overall free body diagrams and the other forces. Just really concerned with the interaction between the fluid and this. So now, as you might have guessed, what I'll have to do is I'll have to take, first of all, let me see if I can, yeah. So I'll have to take like vertical strips, but they will be volume elements instead of being area elements. So you have to understand that ultimately this diagram has to be thought of three-dimensionally. So if I just take an arbitrary strip like this, but actually it's more like a thin plate. I'll explain how it's a thin plate. So think of this object three-dimensionally. If it's some object like this, so I'm basically cutting a strip like this. So it's like a plate. Okay, now this thickness is, let's say, dx. So it's experiencing some force from this side, which is, let's say, df1. Okay, and again, because we are considering a differential element over here, what we can do is the shape of the body, when you look down, when you look at this surface or the surface at the top, the shape is curved. But when you're dividing it into differential elements, this kind of shape, when you divide it into differential strips like this, accordingly, this shape can also be cut like this. This shape can also be cut in this kind of manner. So that kind of thing. So here you will think of this strip like this. If this thickness is dx, and over here also we'll think of it like this, as if this thickness is dx. Okay. Now you can see that here this is at a depth of y from this level underwater. So the pressure difference between these 2 points depends on this y. So if the force acting from this side is df2, okay, so then the vector difference of this df1 and df2, that vector difference is equal to rho gy multiplied by this area, where this area is the area of this section over here. Okay, so it is some dx into whatever this length is, like this. Okay. So now when we look at the net force because of buoyancy, it is basically integration of this df2 minus df1. It is integration of rho g y dA over this entire body. So it is Take the constants outside. To YD. If you look at integration of YdA for this body, you'll realize what that is. It is nothing but the portion of the volume which is submerged. That's very easy to understand because what we've done is we have cut this into slices like this, where this depth for any slice is Y. Okay. Whereas this portion, this is having an area of dA. So integration of YdA is nothing but the volume of this whole submerged part. Because YdA itself is the portion of this vertical plate which is submerged underwater. Because Y part is underwater and this remaining part is above water. So this will be nothing but the volume submerged. So that is like a more general proof of Archimedes principle. Okay, so next up, let's look at some application examples. Of course, floating objects are examples of the application of Archimedes principle and buoyancy. But before we come to the condition of floating, let's look at some interesting type of questions which have been done at the JEE level. All right, so we have, this is basically the cross-sectional view of a cylinder which has a hemispherical cavity below like this. Okay. So just imagine that we have a solid cylinder from which you have cut out a hemisphere from below. So it has a, the lower surface is like an open hemispherical surface. Basically, you had a cylinder like this from which this has been cut out, that kind of situation. Okay. And this is kept suspended partially underwater like this. All right, now the dimensions which are given to us for this are, first of all, the water level is up to only a part of it, it's partially submerged. That is like this. Okay. So this is a solid metallic cylinder with a hemispherical bottom surface, which is this surface here. Okay. So it has a radius r and length L, which is equal to 6r. So this length is equal to 6r. Now the portion which is submerged under water, that is equal to 4R. Okay. And additionally, what is given to us, that the density of the metal is 9 gram per centimeter cube. Okay. And this is of course water, which has a standard density of 1 gram per cc. And let's say R's value is given to us of 4 centimeters. So first of all, we have to find the buoyant force on the metal body. Okay. Then we have to find the tension in the thread, this tension. And now we have to find something very interesting. We have to find the net force on the hemispherical surface due to water pressure. What is the net force on the hemispherical surface due to hydrostatic pressure? Okay, just try this out with me. Yes, anybody got the answers? Amok, the answer is in what unit? Okay, so as far as buoyant force is concerned, we can directly use Archimedes principle. So it is density of water into volume of submerged part into G. Okay. So if you look at it, the portion of the volume which is submerged underwater, that will be the portion that I'm shading over here. This portion, this is the submerged portion. Okay. So if this length is x and this radius is r, then this volume of submerged part, that should be equal to how much? Pi r square x minus 2 by 3 pi r, because there's this hemisphere here. So I believe this x was 4r, right? So it's pi r square into 4r minus 2 by 3 pi r cube. So if you take pi r cube common, it's this much. 10 by 3 pi r cube. That is the volume of the submerged portion. So the buoyant force should be equal to 1 gram per cc multiplied with 10 by 3 into pi into how much was the radius taken? The radius was 4 centimeters, right? Into G if I take 10 meters per second square. So this is what the buoyant force should come out to be.
So,
Yes.
so if you converted the radius into meters, then the density will also become 10 raised to 3.
You can always do that. Oh, sorry. There's also a factor of 10 raised per 3. No, so this I've got in grams now. So this I should write as 10 raised per minus 3. Yes. Because this mass that I've got is in grams. That's the difference. So yeah, so this will become 6.4 by 3 pi in newtons. So that's as far as the buoyant force is concerned. So now the tension will obviously be equal to the weight minus buoyant force. Now the weight will similarly be density of metal into total volume into G. So total volume will be, just replace the X with L. So it's so L was 6R. So it has become pi r cube 6 minus 2 by 3 or 16 by 3 pi r cube. So this is the volume. So the weight, so this will be density of metal into 16 by 3 pi r cube G minus density of water into, this was how much, 10 by 3 pi r cube into G. So this is 16 into density of metal minus 10 into density of water pi r cubed by 3g, this kind of thing. Okay. And then you can substitute and find out the answer finally. But so this will be the tension. Okay. Now the third part is the one which is very interesting, where we have to calculate the net force due to hydrostatic pressure or because of the water pressure acting on the lower hemispherical surface. So just to give you a hint, we don't need to use integration in that. You can just understand that buoyancy is the resultant of the force acting on the lower surface and one more force. Okay, so hope this is clear up to this point. Okay, so just in terms of symbols, okay, this is the value of the tension, or parametrically, this is the value of tension. Whereas the buoyant force is given by this. It is density of water into 10 by 3 pi r cube g. So parametrically, these are the same the values. Okay. Now let's come to the third part. So as I said, we will try to avoid integration, though actually it's a very interesting problem by integration also. But at this stage, let's just understand it like this. Okay. So the only tricky thing is here, we are not finding the net force due to pressure, or rather than the force due to net pressure, we are finding the force due to hydrostatic pressure. So we have to be a little bit careful about the difference between hydrostatic pressure and this thing, and net pressure. So if we are talking about, suppose we are talking about the force due to net pressure. Suppose we are talking about that at the bottom surface. Suppose we take that force as F1. Then what we'd say is, okay, this surface is experiencing a downward force of pressure into area because it's a laminar surface. This is experiencing some unknown force F1, but the resultant of these two forces, F1 minus this, let's say F0, F1 minus F0, that is only equal to the buoyant force. So F1 minus P0 into pi r square would be equal to that buoyant force which we had got, which was density of water into 10 by 3 pi r cube into g. Okay, so you would have said that F1 is equal to this thing. But this is the force due to net pressure, whereas what I want is the force due to hydrostatic pressure. So to consider force due to hydrostatic pressure, now let's consider that as Let's consider that as F2 on the bottom surface. Okay. So this same diagram, now when I consider only hydrostatic pressure, then the force on this surface is 0, because the hydrostatic pressure is equal to 0 at the top, the atmospheric pressure, whereas this is some force F2 which I don't know. So the buoyant force should actually be equal to this force F2. So the force due to hydrostatic pressure alone will come out to be this. So this is the force due to net pressure. This is the force due to hydrostatic pressure. Hope you're understanding this point, okay? Because this upper surface is above water, no? So it doesn't experience any force due to hydrostatic pressure. Okay, now let's also see if we were solving this by integration, what we'd have to do, though it's completely unnecessary as I told you. So if we were solving this by integration, what we'd have to do is we'd have to break that hemispherical surface into differential areas and integrate it, to integrate the force on each of those. So that would be a bit challenging. Okay. So I'll just give you an idea of how to work it out by integration. Try it out yourself. Okay. So the level of water is up to somewhere here, let's say. This we know is 4R. That was at X. This is the symmetry axis. So remember, three-dimensionally, this is a hemispherical surface. Huh? So what we have to do is we have to slice at an angle theta like this, let's say, a strip like this of thickness r d theta. Now that strip will consist of a ring like this. Okay, so that ring will have a thickness of r d theta. It'll have its own radius of r cos theta. So the area of that ring will become this into thickness. So as you are accustomed to doing from center of mass also, this is the area of the ring. Now the thing is, when we consider the net force on that ring, now listen to me very carefully. What is happening is, for the net force on the ring due to pressure, Now within that ring, okay, if you consider a small area like delta A like this, okay, so what is the direction in which the force is acting on that small area because of pressure? It's like this. It's acting radially. It's acting from the center of that hemisphere. It's acting like this from this point, where this point is O, let's say. Okay. So this kind of force delta F is acting, but delta F will be equal to pressure at that point, whatever the hydrostatic pressure is, into delta A, where delta is a small area element like this. But once again, you can see that there are cancelling components and adding components. So for each section on that ring, okay, what is happening is our cos component of force is cancelling and sine component of force is adding. So now when I consider dF as the net force on that ring, it is the sum of the sine components of all these delta F's. Okay, so dF is the net force on the ring. Okay. So that net force will be like the summation of all the delta F's sine component. So that will be like summation of pressure into delta A sine component. So P sine theta into summation of delta A's for the entire ring. So that is nothing but the total area of the ring. So it is P sine theta into dA, or it is P into 2 pi r square cos theta d theta into sine theta. Okay. Now what is the pressure? Now for the pressure, we have to know that at that point, how much is the depth with respect to this surface. So the pressure at this point, remember this hydrostatic pressure, so it is rho g y, where now from the diagram you can see what your y is. Your y from the diagram is equal to, yes, so this whole depth is 4r, and this much part is r sine theta. So your y is 4r minus r sine theta. Okay. So now you have to substitute this y over here. You get the pressure as a function of theta, substitute that there, and now integrate for the net force for all the rings. So basically you end up integrating this quantity. You end up integrating P dA sine theta, where P's value is going to be rho gy, where y is this, okay, and dA is going to be this, and you integrate it for all the rings. So theta will go from 0 to pi by 2. So this would be a very complicated way of showing the same thing, which we have just got by the simple analysis that the net force is the resultant of the force on this surface and the upper surface. Now the upper surface is very easy because it's a flat surface of area pi r square. So we actually didn't need to do this integration. We know that the net buoyant force from the statement of Archimedes Principle or buoyancy statement, and we can say that that net force is a resultant of the force on the lower surface and the force on the upper surface. So we avoided this integration altogether. But this is a very good exercise in integration itself. Okay. So you try this out over here. So this del A that I've written over here, this is not the area of the ring. This delta A or del A, it is now a section of the ring itself. Okay. So the ring itself looks like this. So on that ring, you've taken a section like this. This section is of area del A, and that section is experiencing a force in this type of direction. So when you consider a pair of these delta A's or del A's which are diametrically opposite, you can see that the sine component of the forces will add vertically upward, but the cos components will cancel. So that's why the net force on the ring ultimately doesn't come out to be pressure into area, but it comes out to be pressure into area sine component, because the cos components of all those forces, they are cancelling. Okay, so try out this integration later when you are doing a revision of today's lecture. I want to move ahead and just quickly discuss about floating objects before we conclude today's lecture. So the physics of a floating body is very simple. The weight of the body is so less in comparison to the upthrust acting on it that it's able to float without any additional force applied on it, just on the basis of buoyancy. So if this is a fluid of density, let's say this, then a floating body will be such that the buoyant force balanced by its weight. So density of fluid multiplied by volume of submerged part into G equal to the weight of the floating object. This is the condition for floating. Now, additionally, in this condition, we'll see that if the body is solid and isotropic, that means it has uniform density. So it has a density which is, let's say, rho, which is uniform. In that case, we can further reduce this formula. So we can say that the mass of the body will be that uniform density into its total volume. Because obviously in this equation, this is the submerged portion's volume. So anyhow, if it's an isotropic body like that, we can replace the equation that buoyant force balances weight with the equation that density of fluid into volume of submerged part into G is the uniform density of the body into its total volume into G. So in that case, we get a special condition that the fraction of the volume submerged is nothing but the density of the material divided by the density of the fluid. But remember, this second equation is conditional. It is subject to this condition, that is a solid isotropic body. So it has a uniform density. If it was anisotropic or it had some cavities inside or something, then this second equation will not be valid, whereas the first equation will always be valid, where m is of course the mass of the body. Okay. So with these principles, you should be able to solve HC Verma almost fully for hydrostatics. Okay. And many questions from your module also, which are based on buoyancy principle and all that. Okay. There's nothing more really to this chapter, but more and more variations of the applications of these concepts. But with this, we complete the essential concepts of hydrostatics. Okay. So that's it for today's session, people. Wish you all the best.